Good evening to all of you. Today is our week 10, and we are going to discuss the norm of a vector space. First of all, tell me, my voice is clear or not? Can you hear my voice clearly? Just raise your hand if my voice is clear. Okay, it's all right. So, today we are going to discuss what is the norm of a vector. So, let's wait a minute. And I'm going to upload the PowerPoint slides. So we have inner product space we are going to discuss today, and as you know, inner product space is defined by u and v. U and v. In this way, we can slides. So today this is the inner product space. So it is denoted by this type of curly braces that I write. This type of curly braces, it can be represented. So now, before going to start, we are going to discuss some of the previous things that we know earlier in the previous weeks that we discussed. So now up to 7 to 8 slides, we are going to discuss the previous things. After that, we will start our main topic, that is the norm of the vector. So up to 10 slides, these are the previous, these are just the revisions. So let's start the revision. As we know that, and the length of a vector can be represented like v is equal to v1, v in this way. And the norm of a vector, this is called the norm. And in norm means the length of a vector. So the length of a vector can be represented like v under root v1 square, v2 square, and vn square. So this is called the norm of the vector or length of the vector. So as you know that the norm, any length can never be negative. So we say that length can never be negative, or we can say the norm can never be negative. And the norm is equal to 1 if and only if the unit vector is 1. So similarly, the norm will be equal to 0 if and only if v is equal to 0. And if you multiply any constant with this norm, that c is outside, and in this way. So this is similarly, if we have how we calculate the norm, there are some examples. If we have a vector of 5 r to the power 5, so if we are going to calculate the norm, so we take a norm means take a under root and take every square. So 0 square plus 2 square plus 1 square plus 4 square plus 2 square. So add all these things, and that will be is equal to under root 25. That will be under root 25 means 5. 5 5 is 25. That means 25. Similarly, if we have a vector in R3, so a vector is given 2 upon this, and find the norm of this vector. So find the norm. Norm means just take an under root and whole square. So take a whole square of 2 upon under root 7 minus 2 upon under root 7 and 3 upon under root 7. We will take a square and add them. So when we are going to add them, you will get a 17 by 17, that is equal to 1. So these all things we remember in week 6 or week 7, we all things. And the next thing we will study what is the standard unit vectors. So in 2 dimension we have a standard unit vector will be 0 and 1, 1 0 and 0 1. In 3 dimension we have a in R3 we have a standard unit vector 1 0 0, 0 1 0 and 0 0 1. And similarly in n dimension we can represent a unit vector like this. So next thing is this we learn the unit vector. If v is a non-zero vector, then the vector v is equal to v upon norm v, that is has a length 1 and has same direction of v. Then vector v is called the unit vector in the direction of v. This is called the unit vector in the direction of v. This is the formula of unit vector. So the vector v is called a unit vector in the direction of v. This is called the process of finding the unit vector in the direction of v is called the normalizing of a vector. So here let us take an example of to find the unit vector. Here we have given a vector v and verify that this vector has a length 1. So what we did, we know the formula of unit vector to find the unit vector. The formula, if you see the previous slide, this is the formula to find the unit vector. So v upon norm v. So first of all we have given v. We are given v here, and we have to find the norm of v. Norm of v we know how we can find under root 3 square plus 1 square plus 2 square. In this way we can add them. We will get under root 24. So the formula to find the unit vector will be v upon norm v. So v upon norm v, just put it upper side and norm v will be denominator. So we will take a numerator and denominator, that will be is equal to 3 minus 1 2 upon under root 14. So that will be is equal to this 3 upon under root 14 minus 1 upon under root 14 2 upon under root 14. So just this is the unit vector. This is a unit vector. So he says that just cross check whether it is a unit vector or not. So if you are going to cross check, just take the norm of this vector. So when you are going to take the norm, you will get a 1. So it means it is a unit vector. So these all things we learned in previous weeks. This is the distance between two vectors u and v in Rn is equal to distance of u v will be equal to norm of u minus v. So why I am going to discuss these previous things, because of these things we are going to discuss again in this norm. So that is why the distance formula is also there in the norm. The unit vector, every formula is there in the norm. So that is why I'm going to revise you once again. So the formulas are same, but little bit the symbol is changed. So I will discuss these things again in norm. After 10 to 20 slides, I will discuss these things again. You have seen this. So we learned this in week number 6, how to find the distance between the two vectors. If you have two vectors, then the formula of distance will be is equal to norm of u minus v. And similarly, the properties will be distance can never be negative. Distance is equal to 0 if and only if the 2 points are equal. So these are several properties. So there's an example. If there are two vectors, u is equal to one vector and v is equal to one vector, there are two vectors, find the distance between them. So we know the formula to find the distance between them is distance of u v will be equal to norm of u minus v. This is the formula. And we know how to find norm of u minus v, yani subtract every element, 0 minus 2, 2 minus 0 and 2 minus 1. When we subtract, that will be equal to minus 2. So just take the norm. When you take the norm, that is under root minus 2 square, 2 square, 1 square, that will be equal to 3. So now this is Euclidean, and now they will start, and this is the definition of the Euclidean space. This is the definition of the Euclidean space. It says that Rn was defined as a set of all ordered n tuples of real numbers when Rn is combined with the standard operation vector addition in the scalar multiplication vector length. The dot product result, the vector space, is called the Euclidean n space. So similarly, find the angle between two vectors. If you have two vectors, then find the angle between two vectors. That is a formula. The formula is cos theta is equal to u dot v upon norm u norm v. This is the formula to find the angle between two vectors. So let us take an example. If we have two vectors, vector u and vector v, find the angle between them. So we know that first of all we have to find the norm u. Norm u means u dot u. U dot v means just take a square of 4 square, 0 square, 2 square, minus 2 square. That will be equal to 24. Similarly, take a norm of v. When you take a norm of v, that will be equal to v into v. Just take a square of 2 square plus 0 square plus minus 1 square, 1 square. That will be is equal to 66 under root 6. And then find the u dot v, dot product of u and v. So when you find the u dot product, that is 4 multiplied by 2, 0 multiplied by 0, 2 multiplied by minus 1 in this way, and minus 2 multiplied by 1, that will be is equal to 12. So now put all the values in this formula. Put all the values that you found in this formula. That is cos theta is equal to u dot v upon norm of u and norm of v. When you put all these values in this formula, you will get minus 12 upon under root 24 and under root 6. That will be is equal to 12 upon under root 144. That will be is equal to minus 1. So this is the formula. And when is the value cos theta will be is equal to minus 1? When it will happen? Cos theta is equal to minus 1. When it will happen? If you remember the table of the cos theta and sin theta, so you know that cos 180 degree will be is equal to minus 1. So it means theta will be is equal to pi. So this is the answer of this question. Find the angle. So two vectors u and v are orthogonal if and only. Orthogonal means when they are orthogonal, meaning they are on 90 degree. So it means that u dot v is equal to 0. So the 0 vector is said to be orthogonal to every vector. So, and the last thing is dot product, where we know how we can find the dot product. If we have two vertical vectors, we have to find the dot product. Then we can find u dot u1 dot v1, u2 dot v2. Similarly, in this way we can find, if we have we take a transpose of one vector and another vector, then we multiply it. In this way we can find the dot product. So these all things, it is done, the revision is completed. So up to 15 slides, I am counting, there are 15 slides. These are the revisions of the previous weeks. So Mr. Adil, don't worry about, there are not more slides. So these are the previous weeks are there. Now I am going to start from this week. So hopefully you understand what we read in earlier weeks. So our our topic is inner product spaces. So inner product spaces means let u, v, and w be the vectors in a vector space V, and let C be any scalar. An inner product on V is a function that associates a real number uv with each pair of vectors u and v and satisfied the following axioms. So this is very similar to vector space, and if these four properties are satisfied with any of the example, then we say that it is an inner product space. So the property number first is u v will be is equal to vu. no inner product of VU is equal to UV. The second number property will be is equal to U comma V plus W will be is equal to U comma V, U comma W. And the third number property is if we multiply any constant with UV, then the constant can be written as C into U into V. And the fourth property is if we have a V comma V is greater than 0, and V and V will be equal to 0 if and only if V is equal to 0. So these are the four properties that you have to memorize them, or you have to remember these four properties. So now we are going to discuss some examples of the inner product space. So let's see. There is a note. It says that U dot V dot product Euclidean inner product for Rn, and U inner product UV general inner product for the vector space V. And the next thing, a vector space V with an inner product is called a inner product space. So we know that a vector space can be represented like this. All of us we know V means vector space, and it holds all the 5 additional property. It holds all the 5 multiplication property. If you remember, I told you in week 7 or week 8. Similarly, if it is an inner product space, so we say that it holds all the vector property, also hold the inner product space property. So it means that it is called the inner product space. Okay, so this is the symbol to define that the inner product space. So it says that show that the dot product that satisfy the 4 axioms of the inner product space. So this is the theorem. So now this is a question number 1 is there. This is the question number 1. It says that show that the function defines an inner product on Rn where U is equal to this and V is equal to this, and inner product of UV is equal to U1 V1 and 2U2 V1. So for example, let us count it is equation number 1. So it is equation number 1. For example, we assume that. So one by one we have to show all the 4 axioms. So for number 1 axiom, let us start solution. Let us start the solution. Axiom number 1, that is inner product of UV. So from equation number 1 we can write U1 V1 2U2 V2. We can write from equation number 1 as you seen. So we can interchange U and V, we can interchange. Similarly, V and U we can interchange. So here we are going to interchange V1 and U1. So when you interchange these things, so you can write VU because of V appear first. So you can write its inner product of V comma U. So it means our property number 1 holds, it's satisfied. Now going to property number 2, that is if we have in this, we assume that there is a W is equal to W1 W2. So U comma V plus W can be written as, for example, if you assume that this will part for example you will assume that it is a capital V. So from equation number 1 we can write U capital V plus 2U capital V. From equation number 1 we can write, if you assume it is capital V, so you assume it is capital V, we can write in this form. So U1 V1 and capital V1 and U2 capital V2. So in place of capital V2 you can write V plus W, V1 plus W1. So in this way we can write. So now open the bracket. So when you open the bracket, U1 will multiply V1 and U1 will multiply W1. Similarly, 2U2 multiply V2 and 2U2 multiply by W2. So when you multiply these, you will get U1 V1, U1 V1, W1, 2U2 V2 and 2U2 W2. Now we will take separate in the bracket. So let us take it has on one bracket, yani 2U1 V2, and it put it in one bracket, and this will in one bracket. Put this one is in another bracket. So when we put it is in another bracket, so this will be is equal to u1 v1 to u2 v2 in one bracket, and the rectangle one is in this another bracket. So what is this? This will be is equal to, we can write this will be is equal to uv, and we can write this will be is equal to inner product of u comma w. So we can write in this form. So it means our property number 2 will be whole, that is u comma v plus w can be written as u comma v plus u comma w, inner product of u comma w. So now the property number third. Property number third is if we have any constant, that is c u inner product of uv, so we can write from equation number 1, that is c into u1 v1 plus 2 u2 c2 v2. From equation number 1 we can write this. Now we can write also that c u1 comma v1 to c u2 v2. In this way we can also write. And what is this? If you assume that it is a capital U and it is capital U, then it can be written as cu comma v. Similarly, the last property, that is if v comma v can be written as v1 square plus 2v2 square is always greater than or equal to 0, and it is, if you add them, then it is 0 if and only if v1 is equal to v2 is equal to 0. So these are the 4 properties. All the 4 properties are whole. So hopefully you understand how to prove the inner product space. So if you have any question, then you can ask me in the inner product space. So hopefully all of you understand how we can prove the inner product space. So let's proceed further in the question number 2. In the same way, the same manner we will prove that. So let us see another example how we can show uh, to prove that the inner product space. So let's proceed. This is question number 2. It says that let u is equal to x1 x2 and v is equal to y1 y2 and w is equal to z1 z2 be an arbitrary vectors in R square. Prove that inner product of u comma v defined as follows is an inner product of R square. So this is the equation is given, u comma v is equal to x1 y1 plus 4x2 y2. So for let us assume that it is equation number 1. For assume it is equation number 1. So the same way, there is no any different. If you understand the question number 1, so it is the same question. There is no any changing. Only in place of u and v they put the x and y. So there is no any change. You can easily prove all the things. So here again they show they put axiom number 1 one by one. They are going to prove that. So number 1, axiom number 1 will be is equal to inner product of u comma v can be written as x1 y1 plus 4x2 y2. It is given inside the question from equation number 1. It is given. So if we interchange x1 into y1 we can write, and x2 into y2 we can write, y1 into x1 and 4x2 into y2. So we can write in this manner. So if this will be is equal to v comma u. So similarly we can write the second axiom. The second axiom is u plus v comma w. If we take w is any, w is equal to w1 w2. If we take anything, so here we take w is equal to z1 z2. because of we are talking xy, so we take z1 z2. In the previous case we will take w1 w2. So it's up to you. Whatever you want you can take it. So we will take we will write x1 x2 in this way, and we will open the bracket, multiply all these things and separate the brackets one by one. When you separate the bracket, that will be equal to u comma w plus v comma w. Similarly, the third axiom will be if you multiply any constant with c u comma v, that will be is equal to, we multiply c inside, and that will be take the c outside. When you take the c outside, that will be equal to c comma v, u and v. Similarly, the fourth axiom is u comma u, that will be is equal to x u square plus u square, that is greater than or equal to 0, or you can say x square plus 4x square. So there are four axioms are there. In this way we can prove all the four axioms are there. So this is, so next thing is norm of a vector space. So now we are going to discuss the norm of it, as I discussed in a starting slides. So here how we can define the norm. So here let V be the inner product space. The norm of a vector space is denoted by norm of V, and it is defined by norm of V will be is equal to under root of inner product of V comma V. The same thing as we discussed earlier, the same thing is here, only the difference is here we use inner product V comma V. So that's why today I'm going to revise you something. So that's why it's the same, not more than some difference. And similarly, if you remember, I discussed earlier that is a formula to find the cos theta in the previous slides. Now here let's see what is the definition. Let V be the inner product space. The angle theta between the two non-zero vector u and v is given by cos theta is equal to inner product of u comma v upon norm of u and norm of v. The same formula, there is no any change, only we use the inner product. There is nothing. So that is why I discussed in previous slides. There is no change, everything is same. Only in place of where you use the dot product, here you use the inner product. There is no any change. So let V be the inner product space. Two non-zero vectors u and v are said to be orthogonal if and only if u comma v is equal to 0. But in previous, when they are orthogonal, when their dot products are 0. Here in place of dot product you will use the inner product of u comma v which is equal to 0. So there is a question is where show that the function fx is equal to something, gx is equal to are orthogonal, and the function is given by this. So we have to show that these two functions are orthogonal. So if you remember, to show the orthogonal we have to show that their dot products are 0. But in case of this inner product, we have to show that their inner product will be 0. So let's see, it is given the two functions. One function is fx, the another function is x. So just put in formula number 1, just it is given inside the question. So you will write fx and gx, just integrate from 0 to 1. When you are going to integrate, that will be is equal to x cubed minus x square, and just apply the upper limit minus lower limit, that will be is equal to 0. So that's the same thing. Similarly, if you remember the formula of the distance formula of in this in the previous slides I show you, but here the distance formula will be is equal to the distance between two vectors u and v are defined. The distance of u is defined by distance of uv is equal to norm of u minus v, and here norm of u minus v is equal to inner product of u minus v and v minus u. The same formula, there is no any difference. So these all are and this is the example, and say that consider the vectors. There are two vectors u and v. There are two vectors in C square. Compute the inner product of u v and show that u and v are orthogonal. So compute u and v. So what we did, we will find any inner product of u comma v. So we will find any inner product of u comma v, yani we will find 2 plus 3i multiplied by 1 minus I. Yani we will, yani first element, this is first element of this vector, this is first element of this vector. We'll multiply first element to first element, and similarly second element to second element. We'll multiply this, we will get 5. If you multiply this, you will get this 5 plus I minus 5. So it will be cancelled out, 5 to 5 cancel out, and minus I to I cancel out. That will be is equal to 0. It means it is orthogonal. U and V are orthogonal. Similarly, find the norm of U. So norm of U can be defined as, so we have to find that we have a vector 2 plus 3i, this is a vector, and this is the vector 2 minus 3i. Again, we will, because of it is I, so that's why it will take a minus sign. 2 plus 3i, because of it is in complex, so that's we will take 2 plus 3i, 2 minus I. So similarly, we will take 1 plus 5i, and again we will take minus 1 minus 5i, because of it is a complex. So similarly, that will be equal to under root 13 plus 26. That will be equal to 39. So, and the 6c part, we will find the distance of uv. Distance of uv can be found that you will take a norm of uv. So norm of uv can be found, that will be equal to under root 42. So these are the examples. So show that the following functions are not the inner product space. So there is a function, it's given here, and we have to show that whether it is not an inner product space. So what we did here, so we have to check all the 4 properties, as I told you, the property number, axiom number 1, 2, 3, 4. If any one axiom is not fulfilled, then we say that it is not a inner product space. So let us here we check axiom number 1, it is satisfies. Axiom number 2, it is satisfies. Axiom number 3, it is satisfied. We check ourselves. And when we are going to check axiom number 4, we observe that it is not satisfied. So how we can check axiom number 4? So here it says that let us take any value of the vector v is equal to 1 to 1 anyway. So this is equation number 1. So let us take any value of the vector and put this value in equation number 1. So that will be equal to, in equation number 1, when you put 1 into 1, u1 v1, 1 into 1, and then 2 is there, and u2 v2, 2 into 2, because of 2 here, this is u2. So then this is u1, this is u2, and this is u3. Okay, so when we take u1 v1 here, and 2 is given, and u2 v2, and 2 into 2, and u3 v3, and 1 into 1. Very good. So when we are going to add these things, then we will get a minus 6. But according to axiom number 4, that will always be greater than is equal to 0. And if it is 0, then if and only if v1 is equal to v2 is equal to 0. So it means that it is not hold the inner product. So it is not the inner product. So axiom number 4 is not satisfied. Thus this function is not an inner product in R3. So now there are several properties of the inner product. Property number 1 is, it says that 0 inner product of 0 comma v will be equal to v comma 0 is equal to 0. Property number 2, it says that u plus v comma w will be equal to u comma w plus v comma w. Similarly, property number 3 will be equal to, if we have any constant, the constant will be take outside, and norm of length norm of u will be is equal to, we know that and inner product of u comma u can be written as norm of u square. We can write in this way. These all things we learned earlier. This thing we learned earlier. Orthogonal if and only if this value is equal to 0. This all things definition we learned earlier, and this is also unit vector we learned earlier. So what it says, this is a question. It says that if PQ is equal to is an inner product, let PX is equal to and QX is equal to, there are two functions, the polynomial PX2. Find the inner product of PQ. So there are two functions are there, and he have to find the inner product of PQ. So we know that we have to find the inner product of PQ. What we did, we will multiply this is our first element P, and we will multiply 1 into 4, and then multiply what is x. What is the x term here? There is no x term here, so we will use 0 multiplied by 2x, 0 multiplied by 2, because of there is no term x in P. So similarly, multiply x square to x square, that is 2 multiplied by 1. So when we multiply this, that will be is equal to inner product of PQ will be is equal to 2. So what is the second question is, what is the norm of Q? Norm of Q will be is equal to under root Q into Q. So Q into Q will be is equal to, this is Q. So yani 4 square minus 2 square plus 1 square, that will be is equal to under root 2. And find the distance. So distance formula, first of all find the distance. Distance formula is yani this norm of PQ. This is the formula of distance, norm of P minus Q. So first of all find the P minus Q. What is P minus Q? P minus Q, yeah, just subtract P minus Q, just subtract this. So when you subtract this, that will be equal to minus 3 plus 2x minus 3x square. So now P minus Q, just put the values, minus 3 plus 2 minus 3 square, that will be equal to under root 22. So in this way we can find the distance. Properties of norm, these all things we know earlier. So find the orthogonal projection, these, and you will see these examples. So Graham-Smith process is not in your syllabus this time, so I will skip this. So the last question is, show that the following sets is orthonormal. So the orthonormal, there are three vectors are given, and you have to find the orthonormal. So orthonormal means if we are going to show there are two things. First thing is if we are going to show whether it is orthogonal, and the second thing we have to show whether it is normal. Then the combination of these two things is called the orthonormal. So for orthogonal, we will show that v1 into v2 will be is equal to 0, and v1 into v3 will be is equal to 0, and v2 into v3 will be is equal to 0. So v3 will be is equal to 0 for orthogonal. We have to show these three things. And for normal, we have to show that norm of v1 will be is equal to 1, and similarly norm of v2 will be is equal to 1, and norm of v3 will be is equal to 1. So the combination of 1 and 2 is called the orthonormal. So we will show one by one these two results. So our we have a S is given, and 1 to 1 there are three vectors are given. So let's see, v1, v2, v3, there are three vectors are given. So first of one by one we will find the vectors. So let's show that these three vectors are mutually orthogonal. So we will multiply v1. First of all, we will multiply v1 into v2. So when we are going to multiply v1 into v2, so first element to first element, we will multiply 1 by root 2 into uh, into root 2 by 6, and similarly 1 by root 2 into root 2 by 6, and 0 into root 2 root 2 by 3. When you are going to multiply these, you will get minus 1 by 6 plus 1 by 6 plus 0, that will be is equal to, cancel out 1 by 6 to plus 1 by 6, that will be is equal to 0. Similarly, next time we will multiply v1 into v3. So v1 into v3 means our first element to first element, second element to second element, third element to third element, we will multiply. So when we multiply this, that will be is equal to, we will get 2 upon 3 root 2 and minus 2 upon 3 root 2, that plus 0, that will be is equal to 0. So in this way we can find. Similarly, the third thing, we will find v2 into v3. So v2 into v3, similarly we will multiply first element to first element, second element to second element, third element to third element. That's when we multiply this, that will is equal to root 2 by 9 and minus 2 root 2 by 9 and 2 root 2 by 9. So cancel it out. When you cancel out this from this to this, that will be is equal to 0. So it means that these vectors are orthogonal. Now the second point is, we have to show that whether it is normal or not. So we will take a norm of these vectors. So show that each vector is of length 1. So you have to take the norm of v1 is equal to under root v1 into v1, that will is equal to under root 1 by 2 plus 0. In this way, all of the values are 1. So you can say that S is orthonormal set. So it is orthogonal as well as normal, so that it is orthonormal. So similarly, one more example, it says that if we have a within an P3 is an inner product space, we have a, this is equation number 1, and with the standard basis 1 x square is orthonormal. So we know, if you remember, uh, uh, standard bases are, as I told you, that standard bases are 1 0 0 and 0 1 0 and 0 comma 0 comma 1. This is the standard basis for 3 dimension, and the standard basis for 2 dimension will be 0 1 and 1 0. The standard basis for n dimensions will be 1 0 0 0 0, and in this way. These are called the standard basis. So I write, with the help of this, I write the standard basis that v1 is equal to 1 0 0. The second vector will be 0 1 0. Third vector, standard vector, will be 0 0 1. In this way we can write the standard vector. So we have to show that whether it is orthonormal. So as you know, to show orthonormal, we have to show that it is orthogonal as well as it is normal. So for orthogonal, first part, for orthogonal, we have to show that their product will be 0. So if we take that v1 into v2, that's we will multiply, then 1 into 0 and 0 into 1 and 0 into 0, that will be equal to 0. Similarly, this 0, similarly, that 0. Similarly, now we will find the normal. If we find the normal, norm of V1 will be equal to 1, norm of V2 will be equal to 1, norm of V3 will be equal to 1. In this way, we will find the norm. So it is called the orthonormal. So it is the end of today's lecture. Hopefully you understand this. So if you have any question, then you can ask me. Yes, if you have any question. So you don't have any question. You understand everything. Okay, wait a minute. I'm going to take attendance. Just wait a minute. Okay, you can go now and have a nice day and good night and take care.